Diabetes has become one of the most pressing health challenges of our time, affecting over 12% of our population and more than 830 million globally. Despite its widespread impact, early detection remains a critical barrier, with traditional risk assessment methods relying heavily on clinical judgment by our healthcare providers, which can often lead to missing significant factors. This is where machine learning comes in. The power of machine learning can transform diabetes risk classification by uncovering complex patterns in patient data that go beyond what conventional methods can detect. By doing so, we aim for early detection based on indicators and pave the way for more accurate and timely interventions. The methods we used in this study include random forest, XGBoost, neural networks, and stacking models. Random forest is an ensemble method that builds multiple decision trees and merges their results to improve prediction accuracy. What is a decision tree? A decision tree is a flowchart-like structure where each internal node represents an indicator in our data set. And that each leaf that comes from that node represents the outcome, what the indicator does for our diabetes risk. XGBoost is a method that sequentially builds decision trees where each tree corrects errors made by the previous one. Neural networks are a class of algorithms modeled after the human brain. They consist of layers of nodes that can process and learn complex patterns from the data. And stacking models is where we combine multiple different machine learning models and use another model that makes a final prediction based on the errors of the other models and is able to leverage the strengths of different models. In this study, we used the CDC's Diabetes Health Indicators data set, which includes various health and lifestyle factors like BMI, cardiac history, mental health, and socioeconomic data. Since recall was the most critical metric, ensuring that we did not have too many false negatives, minimized false negatives, we focused on optimizing recall. Our final model had a 97% recall, 97% accuracy, 96% precision, and a 96% an F1 score of 0.96. These results altogether demonstrate a strong classification performance. We use confusion matrices to visually compare actual versus prediction classifications, which helped us understand misclassification trends. Initially, our baseline had higher misclassification errors, as seen by the spread of color in the confusion matrix, but after improvements in model tuning and class imbalance, our final model showed a significant reduction in error based on the better spread of color in our confusion matrix. We also used indicators that weren't too correlated, so that didn't affect how our model ran, as seen in our correlation heat map. Our major challenge in this dataset was a class imbalance, where there were significantly more non-diabetic cases than diabetic. And this can lead to models that are biased, and that's what we were seeing in our baseline. So we used SMOTE to generate synthetic samples for the minority cases that could compensate what our machine learning model was learning, along with keeping our majority learning set. This helped balance the data set and allowed the model to better learn the decision boundary between classes. Machine learning can effectively classify diabetes risk and support early diagnosis and treatment. This approach can be integrated into electronic medical record systems such as Epic systems and Oracle Health, allowing for real-time updates on a patient's health and data changes within the patient's health.